Good morning. Every so often we meet someone who tells us something that changes our life. I was fortunate enough to meet an astrophysicist who changed my life, and we're only talking 2 or 3 years ago. She was Australian astrophysicist, and she told me about quantum computing and where it was going to go. She started off by saying, how many, and this is a question for you and to ask others, in a table of 10 people, how many different ways can you set up those people at the settings? So, so you can have everybody in different places, and how many combinations and permutations of those people are there? Well, of course, being very, very clever, I said, oh, it's a lot. I'd say as many as 10,000. And I thought I was being very clever. Of course, the answer is 3.6 million. And that's where we come to exponentials rather than linear. As a human, we think linearly, whereas we really should be thinking, well, we should be able to think exponentially, at least to have some modicum of acceptance of it. It's a bit like the chess game, the fable of when the man who created chess in India, they were so proud of him, the king said, look, I want to give you a gift for giving us such a great game. And he said, well, I want just 1 grain of rice on the first board, on the first square, and then double it on the second, so 2 grains, and then double it again to 4, 8, and so on. The king was outraged. He said, what are you talking about? You deserve more than that. And the man, of course, just said, that's all I want. Of course, by the time they got to the end of the second row, it was all the rice in India. And by the time they got to the 64th, it was immeasurable. It's all the rice that there's ever been and ever will be. So exponential is very important. And it's important for what we're talking about, because quantum computers compute exponentially. They actually they compute with how far the electron is from the nucleus. This is at an atomic level. Where this is going to go in the future, wow, it's unbelievable to imagine. I always tell the story of, if you use an ATM now, or whenever you use an ATM to do a financial transaction, or you send an email or a social media message, all of those things. The fastest computer in China of today, the fastest supercomputer, could actually hack into your transaction and decrypt it. The issue is, it would take the fastest supercomputer of today to crack one transaction. It would take 1,000 million years. So you're completely safe. Everybody's safe. It's an encryption called RSA, which is based on factors. Computers are very, very good at multiplying 2 numbers together. But when you say which 2 numbers multiply together equal 15, they literally go, is it 1? Is it 2? Is it 3? And they go through the whole thing. So that's why it takes 1,000 million years. Because it's linear, not exponential. And a quantum computer, using a thing called a series of quantum gates, a quantum algorithm called Shor's algorithm. Peter Shor's still alive. All these guys are still alive. It's great being in a new technology. You can actually email them. And Shor's algorithm on a quantum computer can hack into every ATM transaction on the planet and decrypt it in 6 seconds. What does this mean? The ramifications that are self-evident. The FBI know this, the CIA know this, the mafia know this. We need to be, in fact, I'm writing a novel about a left-wing group who were the first to execute chores on a quantum computer. It's a novel. But it could be in real life, because whoever cracks chores on a quantum computer will literally be in charge of the financial system of the world. Now, fortunately, we have quantum cryptography where quantum fights quantum. But that doesn't take away from the very tenuous situation we find ourselves in. At the end of this course, you will understand not only the future and the importance of quantum computing, you'll understand the basis of quantum physics. And there's three things you need to understand, and these are exciting, very well tested, very well proven, wonderful theories. Quantum entanglement, superposition, and quantum tunneling. Now, I'll go to them in greater detail in the next chapter, but it's unbelievable stuff. Now, we don't know how it works. Einstein could never work out how it works. No one knows how it works. Maybe we never will. Believe it or not, nature is deliberately not telling us. That sounds crazy, and that's, I'll forgive you if you turn it off and go and do a different course, but it's the truth. Nature is not allowing us to know. We can take good enough measurements to measure these transactions, but nature changes so that we never know. It really is that amazing. So we don't understand it, but we can harness it, we can use it in quantum computers. Now, it's very, very difficult. Don't think you'll ever have you may have in the future, but don't think sometime soon you'll have a quantum computer on your desk, because it has to be at absolute freezing point. The coldest point in the whole universe, this is including the middle of outer space where there's no warmth from any sun, no radiation, thermal radiation from any galaxy, excuse me, and yet the coldest place in the universe is right in the middle of what's called a qubit, which is where the operations take place, because heat is just the jiggling around of electrons and atoms, and that has to stop. Otherwise and this is the problem we have, a thing called decoherence, which we'll explain later, which is why it's taken a while for us to actually build these quantum computers. I will also tell you the mathematics you need to know. If you're young, even if you're old, you've got to study maths to do this. It's going to make it a lot easier. And don't think it's not interesting. Maths has a bad name for being geeky and difficult, and it really isn't. I always use the example of complex numbers and imaginary numbers. Now, there's not a human being on this planet who, on first being told we need to use imaginary numbers, that they thought, right, I have had enough of it now, I'm going to switch off, because it sounds silly. Yet they can be used in calculations. In fact, they are used in calculations, in quantum calculations, because of superposition. And that's where the electron is in two orbits at the same time. It can be in two places at once. Something that we find in fact, everything in the classical world we live in, see, touch, feel, hear, smell, is counterintuitive to the way subatomic particles work. You're a quantum object. Everything's a quantum object. Everything is made up of subatomic particles, and that's the world of the quantum. The quantum world is anything smaller than an atom. And the world acts very differently at that level, totally differently. It's very exciting. We've known this for 100 years, and we're making some wonderful, wonderful advancements. Like your mobile phone uses quantum physics, for example. But we have experiments which we'll go over later, the famous one, the most beautiful experiment ever in science is the double slit experiment. And that's followed by a thing called the delayed choice quantum eraser experiment. And that proves beyond doubt that things can be altered even after they have already occurred. This is well known in the quantum world. We'll teach you about linear algebra, which again is, look, I'm not going to say it's easy, but the fundamentals that you need to know are easy and they're interesting, to be frank. We'll go on then to quantum gates and you'll understand roughly how they work. They're just like logic gates, but they're different. Almost everything in the quantum computing is like totally different. Believe it or not, in a quantum computer, you cannot copy and paste. If you could do that, we'd be home and hosed. You can't copy and paste because to do that, you need to measure the state of the electron. And measurement, and you get used to this phrase, the most important phrase you'll ever learn in any subject is collapsing the wave function. And that came to us from the double slit, and we'll teach you all about that. We'll talk about the different types of quantum computers, like the adiabatic and the ion trap, and there's about half a dozen. And they exist now. Quantum computers exist now, you know, Google, Alibaba, Microsoft, Apple, IBM. In fact, if you just Google any of the global tech giants, and you'll see that they're spending billions on quantum computing. Let me assure you, you will have a professional career for the rest of your life if you follow quantum computing. And the good thing is that old people like me who have been 40 years in computer programming gone out the window. Quantum computers behave totally differently. You have to learn a whole new paradigm so young people will control this world. And then we'll talk about where it's all going, and it's so exciting. Not counting the financial transactions I mentioned before, the advancements in medicine will be incalculable. At the moment, we want to see how medicines work, how they react with proteins and eukaryotic and prokaryotic cells and that sort of thing, DNA. And then, but we can't, current computers cannot, remember they're linear. Classical computers are linear. They cannot cope with this exponential carry-on, whereas quantum computers can. And the real beauty of where we're going with quantum computers is that we don't know. And we don't know because, depending on who you listen to at the moment, we're around about 50 qubits. So we have 50 qubit computers. They're not really true computers. A real true computer needs to be on a thing called a Mariana fermion. It needs to be built on that, which is a particle which is its own antimatter. So it's its own antiparticle, which means they never touch, because you can't have any interference or decoherence. We'll cover all of that, don't worry. But what we need to know is that when we get to 300 qubits, we will be able to map every atom in the universe. Look at a piece of dust, look at your fingernail, take out a little bit of dust. There's a billion atoms in there. Well, 2 to the 300, you know, the exponential 2 with 300 up top, is the equivalent to all the atoms in the universe. So a quantum computer will be able to map that in about a decade or two. What does that mean? I'll say one word: simulation. Talk to you soon. Please enjoy the course. Please, it's a free course, as you know, but there is a follow-up course, the Z2A of quantum computing. I recommend it totally. This is a course that should get you interested. If it doesn't, then you never will. Talk to you soon. Bye.